chain rule is the rule that will allow us to do the most complex derivatives. Okay, so we've done 2x plus 1 to the power of 2x plus 1 all squared, and we expanded it out. But if that's 2x plus 1 to the power of 10, no desire to expand that. And if it's a fraction over a fraction squared, I don't really want to do that one either. So the chain rule is what's going to allow us to work with those more complex functions and allow us to basically take the derivative in a very easy way. Now, I'm going to explain what it means in a minute. So if you have a function as defined as a composite function, okay, a function of a function, the derivative of the overall function is equal to the derivative of f prime g of x, so whatever the derivative of that is, times the derivative of what's inside the function. Okay, using the kind of a hash here with the Leibniz notation, it's the derivative of f of g of x times the derivative of g of x. So we must take the derivative inside that. And using some Leibniz notation, it is going to be dy du times du dx. So the derivative with respect to u times the derivative with respect to x. And we'll talk about that. So you got a function y is equal to f of u, where u is another function. And here's our notation. Okay. So basically, let's do a quick example of this. Let's say we have a function is equal to x squared plus 1 to the power of 10. Okay. So in this case, u is equal to x squared plus 1. So now we have f at u, right, is equal to u to the 10. So we can replace x squared plus 1 with u. So what's the derivative of this? 10u to the power of 9. But, as it says here, that's dy with respect to u. So our function with respect to u, I'll just maybe replace that with y. There's our function with respect to y. But we have to multiply it by our derivative of this, which would be 2x squared, 10x squared plus 1 times 2x. This is your derivative. Okay? And I did miss a 9 there. I don't want to do this. So we do have that notation sometimes where we'll say, as I did in this case, we have y is equal to u to the 10, and u is equal to x squared plus 1. Okay? So the derivative, dy dx, is the derivative of this times the derivative of that. Okay? But we tend to write it in this form more often. But this is the Leibniz notation. Okay? So I'll get a couple of examples for you in a minute. Here's the proof. By definition, dy over dx is equal to the limit as delta x approaches 0 of delta y over delta x. That's our definition, our derivative definition in Leibniz notation. I'm just going to multiply this definition by u over u, or delta u over delta u. Why can I multiply by delta u over delta u? It's 1. Okay? The the ability of multiplication to move, I can make this guy delta y over delta u over delta x. So I just kind of swap places here. That's our multiplication. Our properties of limits, okay, we have a limit of a product. Well, we can write that as two limits of two products. Now, a little bit of a trickery here. This is our definition of our derivative, right? This would be du dx. As our delta x approaches 0, delta u over delta x goes back to this definition that we have up here. But we have this delta x here. There's no x's in this case, right? But as delta x approaches 0, so does delta u. Okay, so there's this idea, if I'm getting closer and closer and closer with my delta x, my delta u is also getting smaller and smaller. So I can then replace delta u, or my delta x with my delta u, and now we have the derivative with respect to u. So there's the proof for it again. So I think of the chain rule as take the derivative of the original function times the derivative of what's inside the function. So here we can think of this as y is equal to the square root of u, and u is equal to x squared plus 1. dy dx is equal to dy du times dx or du dx. So the derivative of this function with respect to u times the derivative of this function with respect to x. So I've done a little bit of substitution here. So I can now use this. The derivative of that is going to be 1/2 u to the negative 1/2. The derivative of that will be 2x. Now, we started in y is equal to x, and we didn't have any damn u's. So let's go back and replace that. We have 2x over, well, we have, what's that?
Isn't there a bottom to it?
Yeah, I'm getting there. Right, x, and then I just crossed off my 2's, and this would be the square root of x squared plus 1. Right, so instead of u to the negative 1/2, I put it here. Now that's one option of doing that. Here's another way of doing it. Our derivative, f prime of x, is equal to f of g, or f prime g of x times g prime of x. It's not another way, it's just different notation. What is the derivative of x squared plus 1 to 1/2? So do the outside function, 1/2 x squared plus 1 to the negative 1/2. So the derivative of the outside function times the derivative of the inside function. And we end up with the same thing. So whenever I see the chain rule, I always apply this outside function, take the derivative of the outside function, leaving the inside function by itself, and then take the derivative of the outside or the inside function, multiply them together, and simplify. Now, this one here is forcing us to do it with this notation because it gives us u, a function of u, y is a function of u, and u is a function of x. And we want dy dx. So dy dx is equal to dy du times du dx. What is the derivative of this function with respect to u? And it's 10 u to the 9 plus 5 u to the 4 times what's the derivative of this function here with respect to x? It is negative 6x. Sorry?
Never mind.
Now, we want this notation here, we want to know what this derivative is when x is equal to 1. Okay? When x is equal to 1, u is equal to 1 minus 3 times 1 squared. So we have 1 minus 3, u is equal to negative 2. So instead of substituting in 1 minus 3x squared in for u, because we want where it's equal to 1, I'm going to substitute in I'm going to take my u, plug it in where I see my u, plug my x where I see that. Big number, and it's going to be negative 5,260 plus 5 times 16, 10 times 8 would be 80 times minus 6, and you get your number from that. I'm wrong. $30,200. Okay, so special case is when we have a function defined u is equal to some function raised to the power of n. This is just going to be n times u n to the minus 1 times du dx. Very simple. Outside function is your u to whatever power. And then you have to take the inside function. This one would be n g of x to the power of n minus 1 times d dx of g of x. It gets complicated, but we'll start with simple. So let's look at this guy here. My inside function is x squared plus 4x plus 6. My outside function is something to the power of 5. The derivative, y prime, another notation that I use, is going to be 5. So there's my outside function taken care of. Now I have to multiply it by the derivative of the inside function, which is 2x plus 4. And that is as far as I'm going to simplify it. Getting the process, maybe not the proof. Now I could apply the quotient law to this. It's a 1 on top. I don't want to really apply the quotient law. So I'm going to write f of t is equal to the negatives for it. Okay. One of the things, if it's just a number on top, I'm going to write whatever's on the bottom as a negative. Okay. So our outside function, bring our -4 becomes our coefficient. Our inside function stays the same. Subtract 1 from your exponent. And then take the derivative of your inside function, which is 2t minus 2. And I took out a common factor of 2 from here, and then just rewrote it with our -5 instead of on the bottom, or our 5 on the bottom instead of our -5. Inside function, then outside function. Okay. When you combine this with the chain rule or the product rule, it can get kind of ugly. Or sorry, product rule or quotient rule. But we just have to approach it in a straightforward manner. So here we have something that we cannot multiply out. It is a product rule question. So let's apply the product rule to this. H prime of x is equal to x squared plus 1 to 1/3 times the derivative of x squared plus 1 plus x squared plus 1 times the derivative of x squared plus 1 to the 1/3. Well, I guess I could have simplified it a lot easier because I could have added them. But, okay. So I just applied the chain rule to what I wanted here. Or sorry, the product rule right now. That's not bad for our first term. X squared plus 1 to 1/3 times 2x, that's our derivative there, that's not terrible, plus x squared plus 1 over here times 1/3 x squared plus 1 to the power of -2/3 times 2x. So here I had to apply the chain rule to get the derivative of this guy. Okay, so that would be the majority of remarks for this. What do you see that's common right now that I could use to simplify this? 2x. I'm going to take out a 2x actually I'm going to take out a 2/3 x, right? Because I don't like that fraction there. Is there anything else that I could take out as a common factor?
X plus ax squared plus the negative 2/3.
Take out that. So we have x squared plus 1 to the negative 2/3. That's going to leave this guy with 3 x squared plus 1 because I took out that 2/3, so I would have a 3 there. And then I would be left with plus x squared plus 1 in that term there.
Oh, wait, 4x squared plus 4. Oh, it's not.
Yeah, so 3x squared plus our x squared, 3 plus r, so that's what it is. I'm going to take out a common factor 4. That'll leave me with x squared plus 1 over x squared plus 1 2/3, which can be then reduced also 8/3 x squared plus 1 to the power of 1/3 because I'm going to subtract my exponents here. As I said, once I looked at that question, I said, I got a better way of doing it, but I wanted to show you the idea of the chain rule included within a product rule. So the product rule said, okay, I got to do the derivative of all this stuff, and now I have to do the chain rule here. Okay? Sometimes I have to do the chain rule first and then the product rule. Like one of the things we would have done yesterday. Well, actually, no, that would have just been a straight product rule chain rule. So you see how complicated it can get, but that's really as bad as it gets. Like, yeah, that's an easy one. I could have tidied that up to x squared plus 1 to the power of 4/3, and it wouldn't have required all this crap. I just did that. Why am I doing it again? Let's try something like this one, which is x minus 6 over x plus 7 to the power of 3. Right? Which we could do, not the worst thing in the world. Okay. Here, I have the outside function first, and then I have a quotient rule in here. Right? So, we'll call that h prime of x. No, that'll be h of x, I should say. So, h prime of x, the derivative of the outside function times the derivative of the inside function. Okay, you see how I'm working through that? This guy stays the same. This one has to do the quotient rule for it. So we have, what's that?
Yours still squared.
No, because we're only looking at what's inside here. We've already dealt with the square or the cube, right? So we're only looking at what's inside that function, the inside function on this case. So you guys understand what I'm saying? Outside function is the cube, the inside function is the quotient. So we have a quotient rule, so that would be x plus 7 times 1 minus x minus 6 times 1 over x plus 7 squared. There should be a squared there.
Yeah.
I thought you were talking about in there. I'm sorry, I thought you were talking about in there. So we end up with 7 minus a negative 6, so we get 3. This will stay the same. We will have 13 on the top here over x plus 7 squared. And let's got that frickin' squared again. Can that be tidied up a little bit?
I hope not.
It can actually. Because I have x minus 6 over x plus 7 all squared. Can I not write that x minus 6 squared over x plus 7 squared? Or one of the laws of exponents say I can do that. Okay. All right, I'm going to just multiply things. I've got 39 x plus 6 squared, sorry, x minus 6 over x plus 7 to the power of 4.
Josh. Yeah.
7? Like the
Yeah,
x
3
is
times
this.
13.
Okay. So where did 13 come from, or where did 39 come from?
39, then I figured it out.
Okay. On a piece of paper, I want the derivative of that, please.
Yeah, I need help, but I have no clue where to start.
Okay, what is the outside function?
The whole thing.
Right? I could say this would be f of u is equal to u to the power of 3/4. Right? And u is equal to x cubed plus x squared minus 2. Okay, what's the derivative of this guy?
3/4.
3/4 u to the power of what?
Negative quarter.
Negative 4th. Okay. Now that would be that, but it's not that, right? So right now y is equal to 3/4 x cubed plus x squared minus 2 to the power of 1/4. That's y prime so far. That's our outside function.
Is it negative quarter?
What's the derivative of the inside function?
3x squared plus 2x.
Okay.
Time.
Because of that 1/4, I wouldn't. I would just write this as 3x squared plus 2x over x cubed plus x squared minus 2 to the power of 1/4. Okay. I'm not going to try to simplify. I'm not going to ask you to expand trinomials by binomials all the time.
Where'd the 4 go? Yeah.
That's
it.
That's as simple as that one gets. Now, if I was wanting to take the derivative of that, we'd have to do the product rule, chain rule again. What would you do here first? Well,
Write it down.
the first thing I'm going to do is I'm going to write it as x plus the square root of x, or x plus x to the 1/2, all raised to the power of 1/2. I hate radical signs. I want exponents. So our outside function is at raising something to the power of 1/2. So y prime would be 1/2. Leave what's inside the function alone. And apply your power rule to that. What's the derivative of the inside function now, Molly? 1 plus 1/2 x to the negative 1/2. Really don't want to go much further than that. I guess I could, but that would be perfectly fine right now because it's got all sorts of things. Okay, so y on your own. Everyone done the first one? So Sean, what did you get? What did you put in for your first step?
First step, took the radical and put x squared plus
Your
x.
next step.
Next step after that?
Yeah.
1/4 times x squared plus x to negative 3/4 times 2x plus 1.
Okay, so there's your derivative of the outside function times the derivative of the inside function. And I would tidy this up to 2x plus 1 over 4 x squared plus x to the power of 3/4. Okay. No other way to really tidy that up. Molly, what's your first derivative here? Or your first step in this derivative?
The derivative of the outside function, so it's negative 3 to the inside function. The negative 4. And then the inside function as a derivative, so that 3 plus 8x.
Okay, 3 plus ax, or 3 plus 8x. And then we have negative 3 plus 8x. And that's how I would tidy that up. So we want to find dy dx. We want to find the slope of this function when x is equal to 4. Well, if x is equal to 4, u is equal to 2. 4 minus the square root of 4. So we'll keep that in mind. Okay? We want dy dx. That's dy du times du dx. So the derivative of the outside function times the derivative of the inside function. So we have 2u minus 10u to the 4th times 1 minus 1/2 x to the negative 1/2. Now, we want an absorb. We'll just plug these guys in where they're appropriate. So we got 4 minus 160. So that becomes minus 156. And that one, 1/2 times, oops, nope, that's supposed to be a 4 there. 1/2 times 1/2 is 1/4, so that becomes 3/4 when we do that. And 3/4 times 156 is 1. Negative 107. Let's take a look at a couple where we have to do chain rule and product rule. And I'll give you some time to work on some more. Everybody got that one copied down? So let's look at one I'll do with you. And then I'll give you one to do on your own. X times, and I'm too lazy to change that, x squared plus 1 to 1/2. Okay. We know it's a product rule, because I cannot multiply that, it becomes a pain in the ass to multiply that in. I can trick it into doing that, but we have the product rule. So it's going to be the derivative of, no, let's say x squared plus 1 to 1/2 times the derivative of x plus x times the derivative x squared plus 1 to 1/2. I like doing this because it reminds me, hey, you got a chain rule problem here in addition to the product rule problem. Yes?
Sure.
You see where there's a chain rule here? Right? We have a function raised to the power of another function. So this becomes x squared plus 1 to 1/2, because the derivative of that is 1, plus x times 1/2, x squared plus 1 to the 1/2 times 2x. And I did lose a negative sign. Okay. Do we see what, okay, so there again, that's product and chain rule as required. Dylan, do you see something that I could take out as a common factor that would make my life a little easier to simplify this?
X squared plus 1 to the negative 1/2.
I take out x squared plus 1 negative 1/2. This becomes x squared plus 1. This has disappeared, and that's become, we now have x squared. However you want to write that. I don't like negative exponents. If I can get rid of them. Okay. Give me, find g prime of x. I usually put it plus 2 minus 3x times the derivative of what
Yeah, I'm lost. Now, what is
So I do see a common factor. So take our x squared minus 1 are 3. But that is correct so far. Right? Then we're going to take our over and then take the derivative. Plus, plus, times the derivative. So that's my basic product. So now this guy, the derivative of this, or x squared minus 1 cubed times that change over here 1. What is this guy? What's the derivative of x squared minus 1 squared? Right, derivative of the outside function. Oh, and then I apply the derivative. I multiply by the derivative. Plus squared minus 1. So now we have, I use something that I don't think one multiply. So I'll take out x squared minus 1 power 8 dx times minus 2x. Squared. Oh, okay. And over here, taking out x squared minus 1 to the cube. So let's get minus 3 x squared minus 1 to the 1 as well. Minus 1 squared minus 5 x. Oh, this product becomes 16x minus 24x squared minus another 3x squared minus 27x squared. Oh. So think about applying your chain rule first. How do you do? I'm going to put my pen on it. Okay, so we went over that here. I think I'll stop the recording now because you're tired of listening to me. Actually, maybe one more. I'll do one more and then I'll give you some practice and we'll spend some time on this tomorrow to practice. We'll do this one. H of t is equal to t squared plus 1 to the 10th over t plus 1. Or that'll be t squared plus 1 over t plus 1 to the 10th. Okay? Now, in this situation, it's very similar to the question I did before. We are going to have a product rule, but I have the chain rule that's going to be applied. Sorry, we're going to have the quotient rule, but I'm going to have the chain rule that's applied first because our outside function is the function being raised to the power of 10. So I've got 10 t squared plus 1 over t plus 1 all to the 9th times the derivative of this, which is going to be t plus, okay, times the derivative of that quotient there. And since I'm running out of space, I'm going to move over here. Leave that guy alone. So we have to apply the quotient rule to this. So that will be t plus 1 times the derivative of t squared plus 1 minus t squared plus 1 times the derivative of t plus 1 all over, over t plus 1 squared. So forget the complicated part. I said, I've done the derivative. Now I got to take the derivative of the inside. That's a quotient rule. Let's apply the quotient rule and just leave that other guy alone. Now I know where I'm going with this, so that's why I have applied the 9 to both my numerator and my denominator. Our function, t plus 1 times 2t minus t squared plus 1 times 1 So to simplify my top, I have 2t squared minus t squared, which is going to give me t squared. I have 2t, and I have a minus 1. And on the bottom, I have t plus 1 to the 9th and t plus 1 squared. What do I end up with? T plus 1 to the 11th. I can't factor that, although I did look. Yes, it looks complicated. It is somewhat complicated. It doesn't get actually much more complicated than that. But going back to your starting point, I have to do the power rule for the, I have to do the power rule on the outside function, and then I have to take the derivative of the inside function. Okay, over here, when I did this one, I applied the product rule first because power rule didn't apply to everything. I applied the product rule, and then I had to apply the chain rule in this case. Break it apart in that. Okay. So your homework will be page 102. We'll go with 1 G H I K number 2 and 6 B D E and F. And we'll go over this again tomorrow. We'll start to make sure, I may want to make sure that you have this down because it is so very important that you have this process down.